One of the most interesting prospects of this project is the methodology used to create the device. Now, as we can see here, the methodology is broken down into 4 main sections. The first main process is the process of calibration. Calibration is a pre-processing step, and the device only needs to calibrate once for a new surface. Calibration is needed because if we take a look at the physical construction of the Kinect, we can see that the RGB and the depth camera are not at the same position, and therefore each camera perceives the environment in a slightly different way. Calibration is used in order to adjust the shift from camera to camera. There are 2 variables that need to be calibrated for the device. The first variable is the XY position shift from each pixel from camera to camera. Because the camera sees the environment differently, there's a pixel shift between where an object stands in the RGB camera and from where the object stands in the depth camera. The second variable that needs to be calibrated is the pixel to length ratio. Because the device may be projected on a slanted surface, the pixel to length ratio from the surface closest to the camera will be different than the pixel to length ratio from the furthest point of the surface. The second stage is the initialization process. In the initialization process, there are 3 main steps. The first step is that the user manually selects the region of interest. The region of interest is the entirety of the projection surface. Selecting the boundaries of the projection allows for the computer device to automatically calibrate the finger position to the size of the computer screen. The second step is to map the surface of the environment of the projection. By mapping and saving the background of the projection, the device is able to know when the finger is touching the surface of the projection, even when an irregular surface is used. The final step is to train the support vector machine classification algorithm. The support vector machine algorithm is initialized by using 2 sets of data. The first set of data is all shapes that look like fingers, and the second set of data is all shapes that are not fingers. In other words, that is image processing noise. Using the support vector machine will allow the device to be more noise resilient. The most important process of this methodology is the third process, which is the finger detection algorithm. The finger detection algorithm consists of 2 main substeps. The first substep is the detection of all objects touching the projection surface. The second substep is the recognition of fingers from the objects touching the projection surface. To detect touch, an approximately 1 cm invisible layer was placed above the projection surface. The characteristics of the projection surface were obtained in the initialization phase. Any objects penetrating this 1 cm layer is considered to be an object touching the surface. From this, a binary image was created with all white shapes representing objects touching the surface. Using this binary image, the support vector machine algorithm was used to classify from these white shapes what objects touching the surface are fingers and what objects recognized are actually just noise. The last process, the 4th phase in the methodology, is the post-processing step. In the post-processing step, a Kalman filter was applied to smoothen the detected movement of the finger. The Kalman filter used is based off 2 variables, the first variable being the XY coordinate position of the finger, and the second variable being the XY vector velocity of the respective fingers. Therefore, noise that does not fit this physical interpretation of the model is removed. So as you can see here, I'm using the Visual Studio's 2010 IDE. Now if you run the program, you'll immediately see that there will be a gray window appearing. The window is gray because the support vector machine is currently initializing. And when it's done, you can see the training data. On the left side, I have just random shapes. And on the right side, I have just noise. And this is for the non-finger classification training. If we take a look at the finger classification training, these are all images taken from the software from previous variants and screenshotted. So if we can compare, we can see there's a stark comparison between both types of data. Now when it's done, you can see that there's 2 windows. The left window is the depth image from the Kinect, and it's black and white. You can see my hand there showing for the depth image, but not clearly. On the right side, you can see the RGB image, and you can compare the RGB to the depth image this way. You can tell from the raw data that it isn't exactly perfect because you can see a bit of noise over there in the depth image. However, what we do is we select the region of interest in this stage, and you can see I'm doing it with the mouse right there, and this determines just the projection itself. So after we select the region of interest, we can see we're immediately brought up to the main process. These are all debugging screens. So all of the screens in total are the RGB camera. This is the depth image color coded, and we got the binary thresholded image. That is what the camera processes. And the data screen just graphs the position of the measured finger. And in this screen, we can see both the raw measurement data and the Kalman filter process data. Now, if I put my finger into the touchscreen projection, you can see in the top left corner the RGB color image that you can see the general shape of my finger indicated with a pink line, and you can also see the center of my fingertip. This is reflected both in the depth image, which is the orange color-coded image. You can see a bit out of my finger there, my hand there, and on the top right, you can see in the touchscreen binary image of objects touching the projection, you can clearly see that there's a white dot, and so this white circle, this white shape is what's being reflected in the RGB image. This is the fingertip, and the center is calculated from there. We can also see from the bottom right the movement of my finger. You can see that the blue line represents the raw measurement data, which is more jagged than the green line, which is the Kalman filter smooth data. Now here you can see I'm using multiple fingers to test multiple touch point. Although Windows 7 only supports one finger, my device can still recognize both fingers, and in this case the whole hand. So we can use we can have multiple touch points with the device if we use an operating system that accepts multiple touch inputs. Now here I'm actually going to skip some of the boring footage, and I'm going to jump right into the use of an application with this device. And so my first example will be the use of Paint with this new interactive projection whiteboard. Now as you see here, I'm drawing straight from my hand, and you can see that it's very curved, very accurate. It can do all sorts of complex shapes, even small changes in the position. Although it's not perfect, there's still some jagged line, and this can be improved. If I'm not running a debugger, if I'm just running the release version, the number of points that's detected is determined by the speed of the program. In this case, having my program run as a debugger, as well as this green cap is actually slowing down the speed and as well as the smoothness of the drawn points. So I'm actually going to skip ahead again, and I'm going to show you an example of using chess with the device. And so chess in this case will be a sense of just point, touch, and touch at different locations. So there's no dragging, it's just point position A, point position B. And so you can see touch, even just point touch, can be recognized really well and also of high precision since I'm actually clicking the tile I want to click. So the last example I'm going to show today is an example of solitaire, and I think that solitaire is a decent example of the application because it shows how the click and drag, like holding onto the card, can be used, and it shows how the device is able to keep track of the card I'm holding right now, so it means that noise isn't affecting the detection, and also means that the card, my fingers being constantly detected throughout the whole entire period, which is important because it shows that if I'm able to hold the card for the entire time, then my device has good recognition and is very noise resilient. You can also see that when I'm clicking the deck, it's just one single touch on the card deck. So in this example, you can see both examples of the click and drag, click and hold, as well as just a single click and representing a touch. So I hope this video is able to provide more insight into the methodology behind my device for the Google Science Fair. And I also hope that you enjoyed the live footage of my device working with various different applications. I've also gotten the device to work with applications not shown here, like being able to sketch, draw in 3D using Google SketchUp. And if there's enough interest, I will post videos of the device with different applications running in the near future. Thank you.